All right, hi everyone. Welcome back to section 7.3. Well, let's go ahead and take a look at some examples of using the first translation theorem. Okay, so we have this function that we want to Laplace. Here we have e to the 5t, t cubed. Okay, so remember the first translation theorem. What does that state? It states the Laplace of e to the at, some exponential multiple times our function. Well, that's just the Laplace of that f of t, just a regular Laplace of that function. And we are we are not, we are translating and shifting SA units. So that's the first translation theorem. So this helps us out with a Laplace transform of this caliber, because this would require integration by parts and it would be very long and tedious to do, but we can use the first translation theorem right now. So let's pick apart a couple of things. So here, 5 would be A, and then t cubed would be our function that we know how to Laplace transform, this f of t in our definition. So let's go ahead and Laplace transform this, but first we're going to use this first translation theorem. So what this would equal is the Laplace of just t cubed, but we need to pay attention to the translation. So s is shifting 5 units to the right. Okay, so what is the Laplace of t cubed? So I have our basic Laplace transforms here. So this would fit into the t to the n category. So t cubed, well, what would that be? That would be 3 factorial over s to the 3 plus 1, so 4. Okay, so maybe you knew that top of your head already, maybe you didn't, but it's good to have a table by you. So let's go ahead and write that down. So this equals 3 factorial over s to the 4th, and you still want to keep your translation. So S is shifting 5 units to the right. So let me just, just in case, recall the Laplace of t to the n is n factorial over s to the n plus 1. Okay, so 3 factorial, that's like, you know, is 3 times 2 times 1. So that equals 6. So this would be 6 over s to the 4th. But remember, we are shifting s 5 units to the right. So the way we would write this is s minus 5 to the 4th. So s minus 5 replaces s. So that's what we mean by translating over the s-axis. We're moving 5 units to the right for s. Okay, let's go ahead and try out the next example, example B. So another Laplace transform that would be very difficult to do using the regular definition. We would need integration by parts, and then we would need to move it over to the left side to combine the integrals, and it would be a long one. But we can use the first translation theorem to make this easier on us. So, let's just rewrite it again. So, first translation theorem is just a Laplace of the function f of t that we know already, and we are shifting s a units. So let's go ahead and try this out. We see that a equals -2, so we're going to be shifting left 2 units. And we see that cosine of 4t is our function that we are going to Laplace, that we know how to already. So using the first translation theorem, the Laplace of this would be just cosine of 4t, but we are shifting s 2 units to the left. So, we could write this minus -2 to make it easier. It's going to end up being +2, but just want to show how that works, okay? And so cosine of 4t, got our handy um, table here, cosine of 4t, right? So that means the Laplace of that would be s over s squared plus 4 squared. Okay, so let's bring that back here. So the Laplace of cosine 4t is going to equal s over s squared plus 4 squared. And then just keep in mind that you're shifting s 2 units to the left. Okay, and just in case, to have it with us here, the Laplace of a cosine is s over s squared plus a squared. Okay, so we could keep moving. And so we're shifting s 2 units to the right. So s plus 2 would replace any s. So s plus 2 replaces s. Think about it as like an input into your function. Some basics of algebra. So this would be s plus 2 over s plus 2 squared plus 16. Okay, and that would be the answer. So this is a good introduction for questions A and B of how to apply this first translation theorem. Okay, it's the same idea in that we need to know our basics of Laplace transforms, but we're just applying this little shifting component to it at the end. Notation helps, symbolism helps, but that's the way we would do that. So with Laplaces come inverse Laplaces, but we'll save that for the next video. So thank you for watching, and I'll see you there. Take care.